Hello students, welcome back to session 2 on chapter number 2, relations and functions. In the last session, we have discussed about Cartesian product of two non-empty sets. Also we have discussed the problems on exercise 2.1. Now we will go to the next topic, that is relations. In our day-to-day life, we come across a relationship between human beings. Like is a father of, is a mother of, is a brother of, is a sister of, and so many relations we have in our social life. Similarly, in mathematics, we can have the relationship between the first element and second element of the ordered pair. For example, let set A is equal to the set containing the elements, say 1, 2, 3. And set B is another set containing the elements, say 2, 3, 4. Then A cross B will have 3 into 3. 9 elements will be there in A cross B. Now, I will define a relationship between the ordered pairs of elements in A cross B, ordered pairs of A cross B. That is, x is less than y. I will define a relationship which contains the elements in the form x comma y, where x must be less than y. X value must be less than y. Means the first element must be less than the second element. Then that set will contain the elements like 1, 2. Of course, 1 is less than 2, therefore 1, 2 belongs to that set. Then 1, 3, 1 is less than 3, therefore it belongs to that set. Then 1, 4, 1 is less than 4, therefore it belongs to that set. Then 2, 2 is not less than 2, therefore 2, 2 does not belong to this set. Then 2, 3, 2 is less than 3, therefore 2, 3 belongs to the set. 2, 4, 2 is less than 4, therefore 2, 4 belongs to that set. Then 3, 2, 3 is not less than 2. 3, 3 is not less than 3. Therefore, 3, 4 is the last element. 3, 4. It belongs to that set. So, here we have the elements in the form x, y, which belongs to A cross B. Here in A cross B, we have 3 into 3, 9 elements. N of A cross B is equal to 9. There are 9 elements in A cross B. Whereas there are 1, 2, 3, 4, 5, 6 elements in this set, where the first element is related to the second element in each ordered pair. That is what we can observe here. X is less than y. First element is always less than the second element. That is the relationship between x and y. The relationship between x and y here is less than. X is less than y. So this is the set. This set is denoted by R. R stands for relation. So R is a relation is given by the set of all x, y, where x belongs to first set, here that is x belongs to A, y belongs to the second set, that is y belongs to B. Set of all such x, y, set of all such x, y is called relation or R. So a relation is subset of the Cartesian product of set A and set B. So R is a subset of A cross B. Relation is a subset of A cross B because each and every element in the relation is obtained from the Cartesian product of two sets A and B, and it has a special property that the first element is related to the second element under the given relationship. Therefore, a relation is defined as a relation R from a non-empty set A to a non-empty set B, because to define the Cartesian product of two sets A and B, the sets A and B must be non-empty sets only. So relation is a subset of the Cartesian product A cross B. It is a subset of the Cartesian product A cross B containing the elements x, y. Relation should contain the element x, y, where x is related to y under the given relation. X must be related to y. Otherwise, it does not belong to that relation. Therefore, relation is clearly a subset of the Cartesian product of two sets containing the elements x comma y, where x is related to y under the given relation R. So, R is equal to set of all x comma y, where x belongs to set A, y belongs to set B, and x is related to y. This is where this method of writing the relation R is known as set builder method or rule method of writing the relation, because relation itself is a set which is a subset of the Cartesian product of two sets. And this method, the same set here, is written in another method where the elements of the set are listed, separated by comma. This method of writing the relation or this method of writing any set is known as a roster method or tabular method of writing the set. So this is the same relation written in two different forms. We can also represent this in this example. We can also represent this using arrow diagram, where this is the set A containing the elements 1, 2, 3, and this is the set B containing the elements 2, 3, 4. Now the relation R contains the elements where x is related to y in set B. X belongs to set A, y belongs to set B. Now you see 1 is related to 2, therefore 1 maps to 2 here. 1 is related to 3 here. 1 is also related to 3. 1 is related to 4 also. 2 is related to 3 because 2 is less than 3. 2 is related to 3. 2 is also related to 4 because 2 is less than 4. And 3 is related to 4 because 3 is less than 4. So 3 is related to 4. So this way of representing the relation is called arrow diagram method. Arrow diagram represents the same relation. So this is a set builder method, this is a roster method, and this is arrow diagram representing the same relation. The second element is called the image of the first element. In this relation R, you can see that the second element is the image of the first element. Here 2 is the image of 1. You can see that in the arrow diagram here. 2 is the image of 1, and 3 is also image of 1, 4 is also image of 1. At the same time, 3 is the image of 2, and 4 is also image of 2. 4 is also image of 3. So, set of all second elements, that means the set of all images is called range. Range is the set of all second elements. The set of all first elements of the ordered pairs in a relation R from a set A to a set B is called domain of the relation R. What do you mean by domain? Domain is the set of all first elements in the relation R. Here we can see R where the first elements are 1 and 2. So domain is having the elements 1, 2 and 3 here. So domain is equal to 1, 2, 3. That is set A here. Set of all first elements in the ordered pairs of R is called domain. And range is the set of all images. Set of all images is called range. Set of all second elements in a relation R from a set A to a set B is called range of the relation R. Set of all second elements are here 2, 3 and 4. Because all the elements here in B are images, therefore they belong to range. The whole set B is called the codomain of the relation. Whole set. Here we don't have any extra element in this example. Otherwise, if there is an element say 5, which is not the image of any element in A, then that also belongs to that codomain of the relation. And range is always the subset of codomain, because all the elements in codomain, all the elements of range belongs to codomain. A relation may be represented algebraically either by the roster method or by the set builder method. An arrow diagram is the visual representation of a relation. That is what we have explained with the example. Now we have an example here, example 7 in our NCERT textbook. let the set A is equal to 1, 2, 3, 4, 5, 6. Define a relation R from A to A by R is equal to set of all x, y such that y is equal to x plus 1. Here, given set A is equal to 1, 2, 3, 4, 5, 6. And relation R is given by, it is a set containing the elements x, y such that y is equal to x plus 1, where x, y both belongs to set A. Relation R is from A to A. That means here we can observe that x belongs to set A, y also belongs to set A. Relation is from A to A. Now the question is, depict this relation using an arrow diagram. Using arrow diagram you have to represent this set. Now if you observe the elements of this relation R is given in the set builder method here. If you list the elements of this, what are the possible values of x? X can take the value 1, 2, 3, 4, 5, 6. When you give x is equal to 1 here, y becomes 1 plus 1, 2. So y becomes 2. When you give x is equal to 2, then y becomes 2 plus 1, 3. Let us give x is equal to 3. Then 3 plus 1, 4 is equal to y. Y value is equal to 4. Let us give x is equal to 4. Then y is equal to 4 plus 1. So when x is equal to 4, y is equal to 5. Let us give x is equal to 5. When you give x equal to 5, 5 plus 1, 6. Y value is 6. And when you give x is equal to 6 here, when you give x is equal to 6 here, y becomes 7, and that y does not belong to set A. Therefore, this element does not belong to the relation R. So this is the relation in roster method. Okay, elements are listed. If you write the arrow diagram for this is set A, this is also set A. Relation is from A to A, where elements of A are 1, 2, 3, 4, 5, 6. And here in set A we have the same set of elements 1, 2, 3, 4, 5, 6. Now 1 is related to 2. 1 is related to 2. Then 2 is related to 3. 3 is related to 4. 4 is related to 5. 5 is related to 6. 5 is related to 6. And the 6 has no image there because image of 6 is 6 plus 1, 7 does not belong to the set A. Therefore, this is the arrow diagram for that relation. Next, write down the domain, codomain and range of this relation R. What is the domain of this relation? Domain is set of all first elements of the ordered pairs. Set of all first elements of the ordered pairs in the relation R. So, domain is equal to set of all first elements. There are 1, 2, 3, 4 and 5. 6 does not belong to domain of the relation because 6 has no image. Next, codomain. Codomain is the set B, set of all elements in the second set, that is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And range of R. Range is equal to the set of all images, or in the ordered pairs we say the set of all second elements of the ordered pairs. Set of all y in x, y. That is set of all second elements here. 2, 3, 4, 5, 6. 1 is not the image here. 1 belongs to codomain, but 1 does not belong to range. So range is equal to 2, 3, 4, 5, 6. This is the range of this relation. Next, example 8, where we have an arrow diagram where set P has the elements 9, 4, 25, and set Q has the elements 5, 3, 3, 2, 1, minus 2, minus 3 and minus 5. Now the question is, write this relation in set builder form. Write the relation in set builder form. In the set builder form, we obtain the condition by which the ordered pair x comma y is obtained. So R is equal to set of all x comma y such that x belongs to set P and y belongs to set Q, and we have to give the condition from which we got the ordered pair x comma y. Here if you observe carefully, 9 is related to element 9 here in set P is related to 3 and minus 3. It is related to 3 and minus 3. Image of 9 is 3 or minus 3. Image of 4 if you observe, it is 2 or minus 2. 2 or minus 2. And if you observe the image of 25 here, it is 5 or minus 5. So from this it is very clear that 9 is the square of 3 or minus 3. Square of 3 is also 9, square of minus 3 is also 9. 4 is the square of 2 or minus 2. 25 is the square of 5 or minus 5. Therefore, x is square of y, or we say the relationship here, that is x is equal to square of y. This is the relationship. Square of y is x, or x is equal to y square. Then second question is, you have to write the relation in the roster form. In roster form we list the elements of the relation R. So in roster form it is 9, 3, then 9, minus 3, then 4, 2, 4, minus 2, and 25, 5, and 25, minus 5. 25, minus 5. These are the elements listed under the relation R. This is the roster form. What is its domain and range? What is the domain? Domain is the set P here. Domain is set P. Domain is equal to set of all first elements of the ordered pairs in a relation R. Set of all first elements is nothing but 9, 4 and 25. 9, 4 and 25 are the first elements of the ordered pairs of the relation R. Then what is the range? Range is set of all images or the set of all second elements of the relation R. Here the second elements are 9, 3, minus 3, 2, minus 2 and 5, minus 5. These are the elements, second elements of the ordered pairs of relation R. Therefore, this is the range. Set of all images is range, and the set Q is codomain of the relation R. Now, here we have a note. The total number of relations that can be defined from a set A to a set B is the number of possible subsets of A cross B. Already we discussed that A cross B has the number of elements is equal to number of elements in A into number of elements in B. Suppose the set A has P elements, set B has Q elements, then A cross B has P into Q elements. Then if you observe the collection of all subsets of A cross B, then the number of subsets of A cross B is given by 2 to the power PQ. That is called power set of A cross B. Set of all subsets of A cross B is known as power set of A cross B, and it has 2 to the power PQ elements. And each element in that power set is a relation. Each element in that power set is a relation. Therefore, number of possible relations from set A to set B is nothing but the number of possible relations, number of possible subsets. For example, let us take A is equal to A comma B. B is the set containing one element, say 2. Then if you go for A cross B, you will get 2 into 1, 2 elements, that is A comma 2 and B comma 2. A comma 2 and B comma 2 are the 2 elements of A cross B. So number of elements in A cross B is 2 into 1, that is equal to 2. Then what are the possible subsets of A cross B? That is power set of A cross B, we say. Power set of A cross B is equal to set of all subsets of A cross B. One trivial subset is empty set, then a single element set containing A comma 2, then single element set containing the element B comma 2, and subset containing both the elements, that is A cross B itself. That is A cross B itself. Set containing A comma 2 and B comma 2 is A cross B. So these are the subsets of A cross B. This is known as power set of A cross B. How many elements are there in this power set? 1, 2, 3, 4. That is 2 to the power PQ. 2 to the power PQ is equal to 2 to the power P is number of elements in set A into Q is number of elements in set B. So there are 4 elements in the power set of A cross B, and hence we can define 4 relations, 4 type of relations from A to B. There one is empty relation, that is here we write set A and here we write set B. A, B, where we have 2 elements in set A and there is only 1 element in set B, and there is no connection. No element of A is related to any of the element of B. This is one relation, that is called empty relation. Then another one is A is related to 2. That is set A, set B, where we have 2 elements A comma B. Here we have 2. A is related to 2, only 1 element. B is not related. This is another relation, second relation. Third relation is B is related to 2. This is set A, set B, having 2 elements A comma B, and set B has element 2. B is related to 2. This is the third relation. And the fourth one is this, where A is related to 2, B is related to 2. Both are related to 2. That is the last one. Here set A, set B. A has 2 elements A, B, and B has the element 2. Here in A cross B, A is related to 2, B is also related to 2. This is the fourth relation. Therefore, this note says that if the set A has P elements, set Q has set A has a P element, set B has a Q element, then A cross B will have P into Q elements, and power set of A cross B has 2 to the power PQ elements, and those many relations can be defined from set A to set B. This is about the number of relations that can be defined from set A to set B. Here we have example 9, where set A is equal to 1, 2, B is equal to 3, 4. Find the number of relations from A to B. Directly we can get the answer. Set A has 2 elements, set B has 2 elements. Therefore, number of relations is equal to number of subsets or number of elements of power set of A cross B. That is, number of relations is equal to 2 to the power PQ, where P is equal to 2 here, number of elements in the first set, Q is equal to 2, number of elements in the second set. Therefore, we have 2 to the power 4 is equal to 16 relations from A to B. Now, exercise problems. Exercise number 2.2. The first question, let A is equal to the set containing the elements 1, 2, 3 up to 14. So that is a given set. A is equal to the set containing the elements 1, 2, 3 up to 14. Then define a relation R from A to A by R is equal to set of all x comma y such that 3x minus y is equal to 0, where x comma y belongs to set A, because the first set and second set both are same here, set A. Now the question is, write down its domain, codomain and range. What is the domain of the relation, codomain of the relation and range of this relation? If we list the elements of this set in a roster method, here we have 3x minus y equal to 0, means y is equal to 3x. We know value of x is 1, 2, 3, 4 up to 14. Then we get corresponding value of y, that y must be in the same set. So let us give x is equal to 1. Then value of y is 3 into 1, that is 3. 3 also belongs to the same set, second set. Next, let us give x is equal to 2. When we give x is equal to 2, y value is equal to 6. Y is equal to 6, and 6 also belongs to set A. Next, let us give x is equal to next element to 3. Then value of y is equal to 3 into 3. It is 9. So 9 also belongs to set A. Let us give x is equal to 4. When we give x is equal to 4 here, 3 into 4, 12. 12 also belongs to the set A. When we give x is equal to 5, 3 into 5 is 15. 15 does not belong to set A. Therefore, that element does not belong to relation R. So these are the elements. For all other values of x greater than 5, we will get the value of y greater than 15. Therefore, those elements do not belong to this ordered pair. Therefore, this is the set R in the roster method. Write its domain. The set of all first elements of the ordered pairs is called domain. So domain is equal to set of all first elements of the ordered pairs. 1, 2, 3, 4. 1, 2, 3, 4. Set of all first elements. What is the codomain? Codomain is equal to set A. Codomain is the second set, that is set A. And range is equal to set of all images or set of all second elements. Range is equal to set of all second elements. 3, then 6, then 9, then 12. This is the range. Let us go to the next problem. Here define a relation R on the set n of natural numbers by R is equal to set of all x comma y, where y is equal to x plus 5. X comma y belongs to n, set of natural numbers, and x must be less than 4. The relationship between x and y is given here. Y must be x plus 5. So R is equal to set of all x comma y such that y is equal to x plus 5, where x and y are natural numbers and x is less than 4. Okay, deposit this relationship using roster form. Write down the domain and range. Here this is similar to the previous problem. Whenever we give x is equal to 1, 2, 3, possible values for x are only 1, 2 and 3. 4 is not less than 4. So only 3 values for x. So R is equal to, when you give x is equal to 1, first natural number, then 1 plus 5 is 6. 6 belongs to second set, that is n. Let us give x is equal to 2, then y is equal to 2 plus 5, 7. That also belongs to the second set, that is n. And let us give x equal to 3, 3 plus 5, 8. And we cannot give x is equal to 4 and more than 4. Therefore, these are the elements of the relation R. And this method of writing the relation R is called roster method of writing the set. And this is set builder method. Write down the domain and range. What is the domain? Domain of R is equal to the set of all first elements of the ordered pairs, or set of all x here is 1, 2, 3. 1, 2, set containing the elements 1, 2, 3. And range is equal to set of all second elements. Set of all second elements here 6, 7, 8. This is the range. Next, go to the problem number 6 in the exercise. Determine the domain and range of the relation R defined by R is equal to set of all x comma x plus 5, where x belongs to the set containing the elements 0, 1, 2, 3, 4, 5. Here R is equal to set of all x comma y value is equal to x plus 5 here. Y is equal to x plus 5, where x belongs to the set containing the elements 0, 1, 2, 3, 4, 5. So we can observe clearly here y value is equal to x plus 5. Let us give the values. When we give x is equal to 0, then x plus 5 is equal to 0 plus 5, that is 5. And when we give x is equal to 1, 1 plus 5, 6. And when we give x is equal to 2, it is 2 plus 5, 7. And when we give x is equal to 3, it is 3 plus 5, 8. When we give x is equal to 4, 4 plus 5 is 9. X is equal to 5, then y is 10. Y is equal to 10. This is the relationship. Here there is no restriction for y. X must be from this set. Determine the domain and range. What is the domain? The set of all first elements is the domain, and set of all second elements is the range. So domain is equal to 0, 1, 2, 3, 4, 5, and range is equal to the set of all second elements. Second elements are here 5, 6, 7, 8, 9 and 10. Question number 9. Let R be the relation on Z defined by R is equal to set of all A comma B, where A comma B belongs to Z. That is set of integers, such that A minus B is an integer. That is a relationship between A and B. A minus B. If you subtract B from A, you have to get an integer. Then A is related to B. That is a relation. So, given relation R is equal to set of all A comma B, such that A comma B belongs to Z and A minus B is an integer, means A minus B also belongs to Z. Must be an integer, means it belongs to Z. Okay. We cannot list all the elements here because it is an infinite set. Because set Z itself is an infinite set. Okay. Find the domain and range of R. What is the domain? Means what are the values of A? What are the first elements we can have here? Okay. A is an integer, therefore we can take any integer here. So domain is equal to Z. And range. Okay. Range is equal to set of all second elements. Range is also any integer set. Okay, because whenever we give an integer here, whenever we give say 0, okay, then its image is any integer here. 0 is related to all the elements, all integers. Because 0 minus any integer is integer, 1 minus any integer is integer, 2 minus any integer is integer. In general, integer minus integer is an integer. Therefore, all the integers in the codomain are images. Therefore, range is equal to Z. These are some problems in that exercise 2.2, and a few more problems are left as a homework to you. You can practice them. Now, we move on to another important concept, that is functions. What is a function? We will discuss with an example. If we write a relation like x 2 comma a, 3 comma b and 4 comma c. Here we can observe that 2 is related to a, 2 is related to a, 3 is related to b. domain, and second element is the range A, B and C. Then this is called a function. So a function is a relation. Function is a relation containing the elements x, y, where no two ordered pairs should have the same first element. No two ordered pairs should have the same first element. And no two ordered pairs means, suppose here 2 has the image A and 2 has the image B. Then if you write the relation R here, then 2 will be the first element for two elements, 2, A and 2, B. Then this is not a function. So no two ordered pairs should have the first element. And all the elements in the domain should have the image. That is the definition of the function. Let us go through the definition now. A relation F from a set A to a set B. Whenever we say relation, obviously set A and set B are non-empty sets. Relation can be, the relation is always the subset of the Cartesian product, and Cartesian product is defined for non-empty set A and non-empty set B. So a relation F from set A to a set B is said to be a function if every element of set A has one and only one image in set B. Set A has certain elements and all the elements of set A should have image, and image of an element is unique. One and only one image must be there. For example, here you have a set A and here we have another set B, and F is the relation from A to B where A has the elements A, B, C. Here we have the elements 2, 1, 2, 3, 4. Suppose A is related to 1, B is related to 2, and C is related to 4. Then F is equal to set of all ordered pairs A, 1, B, 2, C, 4. Here we can observe that a relation F from set A to set B is a function if every element of set A should have image. Here A, B, C, all the elements of the set A have image. So first condition is satisfied. And second condition is that image of one element is unique. Image of an element is unique. One element in set A cannot have two or more than two images. Here A has only one image, B has only one image, and image of C is one and only one. Therefore, this is a function. Then which is not a function? If some element in set A, at least one element in set A, has no image in set B, then it is not a function. That first condition is violated. First condition is that every element in set A should have image. At least one element in set B has no image means it is not a function. For example, suppose set A is equal to the set containing the elements A, B, C, D, and set B has the elements 2, 3, 4, where A is associated with the 2, B is related to 3, and say D is related to 3. Then this is not a function. This is not a function because one element in the first set A has no image, therefore this is not a function. This is a relation but not a function. The relation is not a function is this, where set A is equal to say A, B, C, D, and set B is equal to 1, 2, 3, suppose, and set A has the image 1, set A also has the image 2, set B has the image 3, set C has the image 3, set D has the image 3. Then this is a relation but not a function because element A has two images here. No element can have more than one image. One and only one image in set B. Every element in set A should have the image, and the image of an element is unique. It should have one and only one image. A has the two images here. Means if you write this as the ordered pairs, A, 1 and A, 2 appears among the ordered pairs. So these two ordered pairs have same first element. So no two ordered pairs should have the same first element for that relation to be a function. So here A has two images, therefore this is not a function. This is a relation but not a function. So a relation f from a set A to a set B is a function if every element of set A has one and only one image in set B. We can also define a function in terms of ordered pairs. A function f is a relation from a set A to a set B such that the domain of f is A and no two distinct ordered pairs in f have the same first element. A function f is a relation from a set A to a set B such that the domain of f is A and no two distinct ordered pairs in f have the same first element. No two ordered pairs can have same first element. If f is a function from A to B and A comma B belongs to f, means A comma B is an element in that relation f, then f of A is equal to B. It's the method of writing a relation. Suppose f is equal to say A comma B, set of all A comma B such that A belongs to first set, say B belongs to the second set, and all those relations holds true. Then we write f of A, image of A is equal to B. Image of A is equal to B can be written as f of A is equal to B. Image of A under the relation f is equal to B. And A is called pre-image of B. B is the image of A is called pre-image of B. And the function f from set A to set B is denoted as f colon A arrow B. Function f from A to B. Here we have an example. Let n be the set of natural numbers and the relation R be defined on n such that R is equal to set of all x comma y, where y is equal to 2x, x and y belongs to set of natural numbers. The question is, what is the domain, codomain and range of this relation, and also is this relation a function? We have to verify. So relation R is given by set of all x comma y such that y is equal to 2x. X and y are the elements from the set of natural numbers. Then here we can also, whenever we give x is equal to a natural number, y will be immediately 2 into that natural number, and that is always an even number, even natural number. So what is the domain? Domain is the set of all natural numbers. We give all the natural numbers to x. Okay. So domain is equal to set of all natural numbers n, and codomain is equal to, codomain is also set of all natural numbers. Y also belongs to n. X belongs to domain, y belongs to codomain. Y belongs to n. Therefore n is the set of natural numbers. And what is the range? Range is equal to set of all even natural numbers. Set of all even natural numbers, because whenever we give a value to x, y becomes 2 into that natural number. It is always even number. Means image of 1 is 2, image of 2 is 4, image of 3 is 2 into 3, 6. So only even numbers in the codomain are images here. Is this a function? Is this a function? If you observe the arrow diagram, the relation is from n to n. In n we have 1, 2, 3, 4 and so on. It is an infinite set. In the codomain also we have infinitely many elements. It is also set of natural numbers. Now, 1 is related to 2. Image of 1 is 2 according to the given relation. 2 is related to 4. Here. 3 is related to 6 next, and so on. So every element in the domain has an image, and each element in the domain has one and only one image. Image of 1 is unique, image of 2 is unique, image of 3 is unique, and every natural number has unique image. Therefore, this is a function. This is a function. Okay. This is about the function, and we can also observe that the cross product of two sets A and B, Cartesian product of two sets A and B is this set, suppose, then relation is a subset of that. Relation is a subset of the Cartesian product of two sets, and function f function is the subset of relations. So every function is a relation, but every relation may not be a function. Every relation is a subset of the Cartesian product of two sets, but all the elements in the Cartesian product may not give the relation. Therefore, we can say that F is a subset of R is subset of the Cartesian product of two sets A and B. With this important concept of relations and functions, we conclude today's session and we'll meet in the next session. Thank you.